We now continue our review of linear algebra. Last time, we looked at the dot product between two vectors. What we'll do today is to build upon this to get products between vectors and matrices and matrices and matrices. This is crucial to modeling linear functions, which are among the most common functions that we'll be using in this class. So what are linear functions? And while we're at it, what are quadratic functions? Well, in one dimension, a linear function of one variable x is something like 3x plus 2. And a quadratic function is similar, except that it's also allowed to have a squared term. So it can be something like 4x squared minus 2x plus 6. But what about in higher dimension? Let's say we're in 3 dimensions, for instance. In this case, a linear function is a sum of a bunch of terms, and each term is either a constant, like 4, or is just a multiple of one of the variables. So we end up with something like 3x1 minus 2x2 plus x3 plus 4. A quadratic function is also just a sum of terms, and each term is either a constant or a linear term, or it could be the square of one of the variables, like x1 squared or 6x2 squared, or it could use the pairwise product of two of the variables, like this term over here, minus 2 x1 x3. Okay, so this is what linear and quadratic functions are for higher dimensional data. Now, we'll be making very heavy use of linear functions. For instance, a lot of the methods we study, support vector machines, logistic regressions, and so on, are based on linear decision boundaries. Okay, what exactly are these? Well, suppose we have data in two-dimensional space. Then a linear decision boundary is just a line, something like the line shown over here. And what we would do with this decision boundary is one side of the boundary would be classified as plus, and the other side would be classified as minus. Now, what is the equation of a linear boundary like this? Well, this is in 2D, so it's just a line, and this particular line has the following equation. 4x1 plus 3x2 equals 12. Let's check this. Okay, so this is the x1 direction here. This is the x2 direction. Let's check this particular point. So this is the point 3, 0. Does it lie on this line? Well, 4 times x1 plus 3 times x2 equals 12. Yes, it lies on the line. Now let's check this point. 0, 4. Does it satisfy the equation? Yes, it satisfies the equation as well. So this is indeed the line, the red line shown in the figure. So this is in 2 dimensions. What happens in d-dimensional space? What does a linear boundary look like there? And it's a direct generalization of the previous form. Okay, so when we're in d-dimensional space, then x is a vector with d components, x1 through xd. And a linear boundary, a linear separator, is something of the form some constant w1 times x1 plus some constant w2 times x2 plus all the way to some constant wd times xd equals some other constant c. Okay? This is the form of a linear separator in d-dimensional space. Now, if you look at the left-hand side of that equation, it looks a lot like a dot product. Okay? And in fact, it can just be written as w dot x equals c, where w is the d-dimensional vector of coefficients, w1 through wd. So dot products allow us to express linear boundaries. Let's see another example of this and then generalize a little bit. Okay, so on top over here we have a function that takes a 4-dimensional vector, x1 through x4, and returns a linear function of these 4 features. Okay, so let's see what we have here. We have f of x1, x2, x3, x4 is, let's go ahead and write it as a dot product. Okay, so the coefficient for x1 is 3. The coefficient for x2, there is no x2, so let's make that a 0. the coefficient for x3 is -2, and the coefficient for x4 is 0. So it's this dot x1, x2, x3, x4. This is how we write down this linear function using a dot product. Now let's look at this second example over here, which is a little bit of a generalization. So now again, we take a four-dimensional vector, but this time instead of spitting out just one number, we are spitting out three separate numbers. The output is a three-dimensional vector, and each of the dimensions is just a linear function of x. Okay, so let's see how we would write that. So we take, this is a function that maps x1, x2, x3, x4 to 4, -1, 0, 0 dot x. So this is x over here. The second coordinate is just x3, so that's 0, 0, 1, 0 dot x. And the third coordinate is -1, 0, 0, 6 dot x. This is the function that we're talking about. Okay, so we can write this in a more convenient form using matrices. So our first row is 4, -1, 0, 0. The second row is 0, 0, 1, 0. The third row is -1, 0, 0, 6 times x, which is x1, x2, x3, x4. We have expressed it as a matrix times a vector. Okay? So let's just go ahead and talk in a little bit more, in a slightly more abstract way about this matrix vector product. How exactly does one multiply a matrix by a vector? Okay, so let's say we have a matrix that's R by D. That means that it has R rows and D columns. So we have this matrix M. It has R rows. Let's call them M1, M2, all the way to M sub R. So we have R rows, and each row is a d-dimensional vector. So each row has length d. We want to multiply it by a vector. The answer in this case is simply the first row dot producted with the vector, the second row dot product with the vector, all the way to the rth row dot product with the vector. So we start with a matrix that's R by D. We multiply it by a vector, which is D by 1. It has D entries, and the result is R by 1. That's the matrix vector product. It's just a series of dot products. Now, a matrix vector product captures a linear function, as we've seen, and the simplest possible linear function is just sending x to itself, the identity function. What matrix realizes that function? Okay, that's the identity matrix. It's a square matrix. If the vector x is d-dimensional, it's a d by d matrix, and it has ones along the diagonal and 0 everywhere else. Okay, so if you take the identity matrix and you multiply it by any vector x, you get back the same vector. Very simple linear transformation. Now, we will sometimes be using identity matrices in several different dimensions. And so in those cases, we'll often use this subscript to denote what specific size identity matrix we're referring to. Okay, so I sub d means a d by d identity matrix. Now let's move on to matrix products. So multiplying one matrix by another matrix. How do you do that? Okay, it's a very simple rule, and again, it's built out of dot products. Okay, so we start with a matrix A, and in this case, we have one that is R by K. So that means it has R rows and K columns. So let's number the rows A1 through AR. R by K. Then we have a matrix B, which is K by P. That means that it has P columns. Let's go ahead and number the columns. Let's call them B superscript 1 all the way to B superscript P. So this is a K by P matrix. The result of these two is going to be an R by P matrix. So the result, which is A times B, is going to be an R by P matrix. Okay? And the ij entry of that matrix, so if you look at the entry in row number I and column number j, that entry over there is A sub I dot product with B sub j. The ij entry of AB is simply the dot product of the ith row of A with the jth column of B. Okay, so in order to compute the product, we simply take a bunch of dot products of every row of A with every column of B. Now what this means is that if you want to multiply two matrices, the inner dimensions of the two matrices have to agree. We need a K in both these positions. And the product matrix, the size of that matrix is given by the outer dimensions. So we take R by K and K by P, and we get something that's R by P. Okay. Let's do a little example of this. Okay, so let's take any matrix A, maybe 1, 2, 3, 4, 5, 6. Let's multiply it by some matrix B. How about 1, 0, minus 1, 0, 2, 1. Okay, so what are the dimensions here? Well, this is 2 by 3. This is 3 by 2. And indeed, the inner dimensions agree, as they must. What is the product? What's going to be the size of the product? Well, it's just given by the outer dimensions. It's going to be 2 by 2. So let's make space for that. The answer is going to be some 2 by 2 matrix. So we have 4 numbers to fill in. What are those 4 numbers? Well, we take the first row of A, which is this row, and we take the dot product with the first column of B. So let's see what that is. It's 1 minus 3, so it's negative 2. What number goes in the second position? We take the first row of A, dot product it with the second column of B. So we get 0, 4, 3. We get 7. 2 more numbers to fill in. We now move on to the second row of A. We take the dot product with the first column of B. So that's 4 minus 6, which is negative 2. And the final number is 4 times 0 plus 5 times 2 plus 6 times 1, which is 16. So that's the product of these two matrices. Very simple. So here's the formula again, the formal expression for the product of two matrices. The ij entry of the product is just the dot product between the ith row of A and the jth column of B. Now there are some important properties of these products. The first is that when you multiply something by the identity matrix, it does not change. That's to be expected. The second is a rather interesting one. So it says that if you take the transpose of a product, it's like taking the product of the transposes but with the flipped order. Okay. Now this is something that you can check by just plugging in the definition of the product, by just plugging in this summation you see over here and just checking that the left and right hand sides really work out correctly. But why don't we at least, as a basic sanity check, just at least check that the dimensions of the two sides are the same. Okay, so what is the dimension of AB transpose? Well, we've already seen that in this case, if A is R by K and B is K by P, then AB is R by P. So AB transpose is switching the rows and columns, so the dimension of it is going to be P by R. Okay. Now let's look at B transpose A transpose. B transpose has dimension B by K. A transpose has dimension K by R. So good, you can actually multiply them since these inner dimensions agree, and the result will have dimension P by R. So at least it's the right size. And it turns out that these two matrices will also be identical. Now for this last one, what we're being asked is that we have these two vectors, u and v. So we have u, a d-dimensional vector, and we have v, a d-dimensional vector. What is u transpose v? Okay, so let's compute the transpose of u. So we just take that column vector and make it into a row. So u transpose v is equal to u1 to ud multiplied by v1 to vd. Okay, so we take each row of the first matrix and multiply it by each column of the second matrix. Oh, it's just the dot product of u and v. So this is interesting. We have two ways of writing exactly the same thing. The dot product of two vectors, u dot v, is exactly the same as u transpose v. And so this is a useful fact to remember. It's something that we'll be using to simplify a bunch of calculations later on. Okay, so u transpose v is just the dot product between u and v. Let's look at a couple of examples. Okay, so now let's say we have a d-dimensional vector x. So x has got d numbers. What is x transpose x? Well, we just saw this. It's the dot product of x with itself. And what's that? That's just the squared length of x. So x transpose x is just a number. It's the squared length of x. What about x transpose? So x transpose. So let's see. X is this vector. So x is d by 1. X transpose looks like this. It's 1 by d. So the product is d by d. It's a big matrix. Okay, that's a little strange. What is the ij entry of this matrix? It is xi xj. So it's the d by d matrix of all pairwise products of features of x. So these are also two very useful things to bear in mind. X transpose x versus x transpose. Now they look almost the same, but as you can see, they're completely different. One of them is just a simple number, the length of the vector squared, and the other is a full d by d matrix. Okay? So one of the things this really goes to show is that you cannot change the order in which things are multiplied. Okay, and so this is a very general and important property of matrices. In general, matrix multiplication is not commutative. AB is not the same as BA, okay, unless you get lucky. Okay, so let's look at these examples, for instance. So here we have two matrices, A and B, and let's multiply them one way and multiply them the other way and see if we get the same answer. Okay, they're both square matrices, so we know they're both 2 by 2, and so we know the result will be 2 by 2. Let's see what we get in this case. So we get 1 plus 2, that's 3. 0 and 0 is 0. 0 and 1 is 1. 0 and 0 is 0. Okay, so that's the first product. The second product is 1, 2, 1, 2. They are completely different. They aren't even close. Okay, so this is something to be a little bit careful about. You cannot switch the order in matrix multiplication. One thing you can do, however, and something that's very convenient, is that when you're multiplying together a bunch of matrices, you can decide which pair of multiplications you're going to do first, as long as you keep them in the original order. For example, you can decide, okay, you have to multiply together A, B, C, D. Why not do AB first, and then do CD, and then multiply them together? That's allowed. Or you can do BC first, and then multiply the answer by A, and multiply that answer by D, and so on. Okay? So you can parenthesize the expression in whatever way you like, as long as you maintain the order of the matrices. Let's look at a little example of this. So here, let's say we have a vector x whose length is 2. What is this huge expression over here? Okay, so clearly there are a lot of things to be multiplied together. But parts of it look familiar. We've seen these sort of things before. X transpose X, XX transpose. What are they? Okay, X transpose X, that's a D by D matrix. Okay. XX transpose is the D by D matrix. X transpose X is just a number. Which do we prefer? The number. That seems a lot simpler. So let's do those first. Okay, so we'll take X transpose X. We know that's just the length of X squared. Oh, here's another X transpose X. That's also the length of X squared. And here's another one and another one. And so what we end up with is the length of X to the power 16. And we're told the length of X is 2, so this is 2 to the 16. Okay? So the associative rule can be very helpful in simplifying matrix products. Okay? We simply choose the products that turn out to be very simple and do those first. So that's it for our second installment of linear algebra. We now have all the notation and tools we need to be able to model linear functions, which is something we're going to be using very heavily in this course.